Introduction to Distributed Computing with TensorFlow. Distributed computing with TensorFlow refers to the process of distributing model training and inference across multiple devices or machines to accelerate computation, handle large datasets, and scale machine learning tasks. TensorFlow provides a comprehensive framework for distributed computing, allowing developers to leverage distributed training strategies, parallelism, and resource management capabilities. Let's dive deeper into the key concepts of techniques involved in distributed computing with TensorFlow. First one is distributed TensorFlow architecture. TensorFlow's distributed architecture consists of multiple components that work together to distribute computation across devices and machines. Some of the key components include worker nodes. These are the machines or devices where TensorFlow computations are performed. Worker nodes can be CPUs, GPUs, or TPUs, and they can be distributed across multiple physical or virtual machines. Parameter server (PS). In some distributed TensorFlow setups, parameter servers are used to store and update model parameters during training. They act as a centralized repository for model weights and gradients. Cluster spec. TensorFlow uses a cluster specification to define the layout of worker nodes and parameter servers in the distributed setup. It specifies the IP address and ports of all the nodes in the cluster. The second one is distributed training strategies. TensorFlow supports various distributed training strategies to accelerate model training and handle large datasets. Some common distributed training strategies include data parallelism. In data parallelism, the dataset is partitioned across multiple devices or machines, and each device computes gradients independently using a subset of the data. Gradients are then aggregated across devices to update the model parameters. Model parallelism. In model parallelism, different parts of the model are computed on different devices or machines. This is useful for large models that cannot fit into the memory of a single device. Pipeline parallelism. Pipeline parallelism divides the computation graph into stages, with each stage running on a separate device or machine. Data flows through the pipeline and computations are overlapped to improve throughput. The third one is TensorFlow's distributed execution. TensorFlow's distributed execution engine handles the distribution and coordination of computations across worker nodes in a distributed setup. It includes features such as distributed sessions. TensorFlow provides distributed sessions objects that manage the execution of TensorFlow graphs across multiple devices or machines in a distributed setup. Distributed optimizers. TensorFlow includes distributed versions of popular optimizers, example Adam, SJD, that can handle distributed training scenarios efficiently. Fault tolerance. TensorFlow's distributed execution engine includes mechanism for handling failures and retries, ensuring that computations continue even in the presence of node failures or network issues. The fourth one is deployment and configuration. Deploying and configuring distributed TensorFlow setups requires careful consideration of factors such as network topology, device placement, communication overhead, and resource allocation. TensorFlow provides tools and APIs for configuring and managing distributed setups, including tf.distribute.Strategy. TensorFlow's distribution strategy API provides a high-level interface for distributing competition across devices or machines. It supports various strategies such as mirror strategy, parameter server strategy, and multi-worker mirror strategy. Next one is the TensorFlow Extended (TFX). TensorFlow Extended (TFX) provides end-to-end tools and platforms for deploying and managing production ML pipelines, including distributed TensorFlow setups. Distributed computing with TensorFlow enables developers to scale machine learning tasks across multiple devices or machines, accelerate computation, and handle large datasets efficiently. By leveraging TensorFlow's distributed training strategies, execution engine, and deployment tool, developers can build and deploy distributed machine learning models for a wide range of applications, from training deep neural networks on a large scale datasets to deploying real-time inference services in production environments. Understanding the key concepts and techniques of distributed computing with TensorFlow is essential for effectively harnessing the power of distributed systems and scaling machine learning workflows to meet the demands of modern applications.